So regular polygons. First, what's a polygon? A polygon is a shape, a closed shape that has many sides, 3 or more, okay? We talked about a couple of different polygons last class. We talked about triangles and we talked about quadrilaterals, right? So now we are looking at different kinds of polygons that have more than 3 or 4 sides. And then we're going to focus more on the types that we call regular. Now, regular polygons are special because they have all sides and all angles equal. And we are talking about the angles at the corners. So these angles are going to be equal for regular polygons, and also their sides will be equal consequently. Now let's do some naming of these polygons. They would have a prefix for the number of sides they have, and this prefix comes from Greek letters or Greek prefixes, and then we just add the suffix gon to it. So, for example, the name of a triangle under this pattern is going to be a trigon, but we call it a triangle. It has a special name, okay? A trigon is still a triangle, okay? So let's put trigon. And then remember that's not really what we use for it. We use triangle. A tetragon, yeah?
This is happening that they all to be equal sides. Could a trigon be a triangle, but a triangle doesn't be a trigon?
Trigons and triangles are the same thing. When you put the word regular in front of it, those are the ones that have equal sides and equal angles. Okay, so a regular triangle is an equilateral triangle, right? A regular quadrilateral is going to be the square, right?
Okay, everybody just said it.
Yeah, we just because it has a name, right? So all of the ones don't really have special names, and then you will recognize their special names as we get to them. But the triangle and the square, they have their own special name, okay? So tetragon would be the square. And then from here on, we will be going to 5. These two have special names, right? And then from 5, we go. Pentagon. You know pentagons, right? And then 6, hexagon, sometimes sexagon, but we don't really use sexagon because it sounds a little bit weird, right? Hexagon, but they're both acceptable for math. So we have hepta for 7, heptagon. And then we have octagon for 8 sides, 8 angles. So far we've done penta, hexa, hepta, octa. We are now to nona, nonagon. Decagon. Undeca or hendeca for 11. And the last one for the number 12 is dodeca. So you only need to memorize these ones from 5 all the way to 12 because the 3 and 4 you already know their names, right? So make sure you know the names, especially for the unde and dode. Okay, unde 11, dode 12. Okay, and here's a triangle, the square, pentagon, hexagon, heptagon, octagon, nonagon, and decagon. And you notice that the more sides your polygon has, the more it's gonna be harder to draw as a broken, right, shape like this with angles. It's gonna get closer and closer to an actual circle, right? It'll be really, really close. So yeah, we will do a little bit of work with these. Yeah. Homework booklet or notes booklet? The homework booklets are at the back of the book. Yeah, you didn't get them last class, yeah. So the next part is looking at the number of diagonals in a polygon. Now remember when we did rectangles, let's take a rectangle or any other quadrilaterals, we said that diagonals are uniting two non-consecutive vertices. But the only two non-consecutive vertices we have, or the possibility of those, would be the opposite vertices, right? Because these two would be adjacent, so you couldn't unite them, right? And this would be the non-consecutive one. So then you would draw the diagonal over there. And then you would have these two as well that are non-consecutive. And that's what they call diagonals. And honest to God, until I was a teacher, I thought diagonals are only two all the time. Until I had to teach this too. And I was like, oh, wait a minute, there's more than two for other shapes, you know, because you don't really focus on a lot of other shapes when you are part like in school, so you don't know. So there it is. There's a pentagon, or the 1, 2, 3, yeah, a pentagon shape here. And there's one diagonal, two non-consecutive, but I can draw another one over there. And I can draw another one over there. So always uniting non-consecutive vertices. I can do one over there. I can do one over there, and I'm pretty much done. How many diagonals this pentagon has? Can you count them? 1, 2, 3, 4, 5, 1, 2. This is done. 3, 4, 5. I think 6. Is that right? Did I count them all? 1, 2, 3, 4, 5. That's right, because this one I counted twice, right? Are there any more? No, right? We drew them all? Yeah. Now, imagine now drawing diagonals for a decagon, right? It gets crazy. And imagine counting them. It's hard as it is to count them for a pentagon. Never mind, you know, if you go to higher and higher number of sides, right? Good luck. So what we did is we noticed that there's a pattern in the number of diagonals as you go up in the number of sides. So the pattern is that if you take n, the number of sides, you can calculate the number of diagonals by doing this formula. N times n minus 3 divided by 2 always gives you the number, the total number of the diagonals a shape will have. So let's test it for the pentagon, because we said it was 5, right? So if a pentagon has n equals 5, right, which is 5 sides, 5 times 5 minus 3 divided by 2, 5 times 2 divided by 2, which is 10 divided by 2, which is 5, right? 5 diagonals. So we were right. We counted them correctly. Let's do one more. Determine the total number of diagonals in an octagon. Now, here's where you have to know the names and how many sides they have. Octagon is a polygon that has how many sides and angles? Is 8, because we noticed the octa is the prefix for 8. So then we plug in into the formula, 8 bracket 8 minus 3 over 2. 8 times 5 over 2, 40 divided by 2, which is 20 diagonals. Total number of diagonals in a regular 25-gon. So every time we're going to go over the 12, because I didn't ask you to memorize anything beyond that, we're just going to put the number of sides as a number. So 13 gone, 14 gone, and then you know that's how many sides it will have, okay? There are, yes. There's a lot of prefix because like any other language, Latin language has a word for all of their numbers. So you would just borrow those words for numbers, right? But then you have to like learn Latin, what's the point, right? Okay, so 25, that means n is 25. So 25 minus 3 divided by 2. 25 times 22 divided by 2. Mental math for this multiplication without the calculator. Here's a trick you can do. 550, you said? Yeah, you're right. So the way you can do mental math for this one, you take the 25 and the 22 and you split it into tenths and units. So 20 and then 2 makes 22, and then 20 and 5 makes 25, and then you just multiply them like that.
Or you just take away 25 times 10 is 250, 500 times 20.
Yeah, that's right. You're great at mental math. Good job. Yeah. Yeah, really good. Yes. So 20 times 5 is 100, and 5 times 2 is 10, and then you just add all of these together, 550. Yes, of course. And if it's not 25, it's like 23 and 7s, and yeah, it gets more difficult. Yeah. Sometimes it's when you get those kind of numbers, you can put more than what you have and then just take it off at the end, right? Does that make sense? So if it's like 17 times 13, you can just do 13 times 20 and then take away that 3 times 13 later on.
Yeah.
You can do that as well. Anyway, so we have 550, we divide that by 2, so we get how many diagonals? 275 diagonals. So make sure this formula is in your study sheet, because you will get a question like this in the test all the time. So 3 marks, so just have to plug in and calculate using your calculator. The next one we do is something that we've done in the past too, in the first lesson, interior and exterior angles, but this time for polygons. We've done them for triangles, right? We haven't really done them for rectangles, but now we can apply them for rectangles and other quadrilaterals as well. So the pair interior exterior angles always happens around the vertex. All you have to do is extend one of the sides, and then you would have a pair of angles that are supplementary to one another, right? Supplementary means they add up to 180 degrees. So you have an interior angle and an exterior angle. Then we're going to do some questions regarding what is the measure of each of these interior angles? What is the measure of each exterior angle that forms outside? What is the sum of all angles in these polygons and such? So let's start with the sum of all interior angles. We have again another pattern that we notice. The sum of all interior angles is a multiple of 180 degrees. And the multiple comes from, again, n minus 2, where n is, what do you think n is again? The number of sides, right? So n is the number of sides or angles in a polygon. So the way the pattern came about, this is interesting because it's really easy to understand, is you can choose a vertex of a certain polygon and then draw all the diagonals from it. Like this. But every time you do so, you are getting triangles. You're shaping up triangles inside the polygon, right? So you would have one triangle right there, another one. The next one is this one, so the third one. And then you have a fourth and a fifth. And in total, how many triangles do we have with this polygon? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the decagon. Okay, and we have how many triangles in it? 1, 2, 3, 4, 5, 6, 7, 8, right? So decagon has 10 sides, and we got 8 triangles. So now the relationship between the 10 and the 8 is 2 less, right? You do that with another polygon, and you notice, oh, it's the same thing. It's always a difference of 2 between how many triangles and how many sides. How does that help me? Well, because I already know the sum of all angles in one triangle, right? So then all of these angles, this one with that one, will count for the one that I need in that corner. This one and that one will make that corner. This one and that one will make that corner, and so forth, right? So all of those will be calculated. And then this one will be calculated in itself. And then all of these tiny ones at the corner, they also will come from the sum of all angles in a triangle. So all of those ones will give you 180 times 2 less than the number of sides. And it will give you the sum of all. How do I count which one? What sizes? Yeah, how do I know it's a decagon? I count the sides. So I start here. 1 side, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. Yeah. Okay, so that's how you come about. Like, this is how the ancients came about all these formulas. Okay, they just try to notice patterns. Can I see a pattern that can connect them all? So when I go through something that I cannot calculate anymore, I can just use that pattern because I'm expecting this to happen, right? And of course, there's proofs that shows that it always happens. The sum of all angles, the interior ones in a polygon, is 180 degrees times n minus 2, where n is the number of sides or angles in a polygon. The measure of one interior angle is pretty simple. Like, if you have the sum of all of them, 180 times n minus 2, which is all of them, all you gotta do is times by how many you have, right? So if it's a decagon, you're gonna divide it by 10, right? And then you're gonna find the measure of a single interior angle. And then all of the exterior angles will be 360 degrees. And then it's gonna be really easy to demonstrate that, because the more sides your polygon will have, the bigger the angles will be. And then the smaller the angles will be on the outside, okay? And again, you'll notice the pattern, it's always gonna add up to 360 degrees, okay? So
they always add up to 1?
all, yeah, always. The exteriors, yes, all shapes 360 for the exterior angles. And that's pretty much it. We're also going to talk about central angles at some point, but let's focus on these few formulas first. So, in a nonagon, find the sum of all interior angles. So for finding the sum of all interior angles, I need to know what n is for a nonagon. Yeah, what is a nonagon? 9, that's right. So it's a polygon with 9 sides. So the sum of all angles would be 180, n is 9 minus 2.
Sounds like it should be like
Nonagon, yeah. Like not a gon, like that. Have you never heard Italians calling their granddaughters nanas? Nana? Well, why? Because they're usually in their 90s, right? They're really old, right? Nana. Yeah, there you go. Interesting, huh? Okay, so what do we get for 180 times 7? Okay, so the sum of all angles for a nonagon is 1,260. Make sure you put degrees because these are angles. Find the measure of one interior angle. So this is all of them. How can I find one of them? Because they're all equal. These are all regular polygons. So that's something that if it's not written here in a regular nonagon, we're going to assume it's regular. Because if it wasn't regular, then the angles wouldn't be equal, right? So we divide by 9. So what do we get? 140. Show why the sum of all exterior angles is 360. So let's show that. Okay, let's show one exterior angle first. How do I get the one exterior angle? That's right, because they are supplementary, right? So one exterior angle measurement, 180 degrees, minus the interior one, 140. So we get 40 degrees for one exterior angle. Now, how many of these ones does the nonagon have? 9. So for a nonagon, we have 9. So 40 times 9, 360. And we showed that the sum of all angles is 360. Find the measure of one exterior angle of a hexagon. A hexagon is a polygon that has how many sides and angles? 6. Okay, again, we're going to assume they're all regular. Okay, so if it's a regular hexagon, we can find the measure of one exterior angle. Now, what information do we need for exterior angles? The sum of all exterior angles is what? 360. Now, if there are 6 of them, how do I find one of them? If 6 of them are 360, how much is one of them? What do I have to do? Divided by 6. Thank you so much. 360 divided by 6, or you can make a formula for yourself. 360 divided by n is 60 degrees. One exterior angle, 60 degrees.
For the C question, you said one exterior angle is 580 degree and the other is 360. So I don't know the difference.
One exterior angle, this one is 40 degrees because if the interior angle is 140, this is not an omegon, but I'm giving you example. 140, the exterior one is 180 minus 140. So you have to do that supplemental subtraction.
Yeah, for this 180,
it's not 180, it's 180 minus 140. It's not it. I didn't stop there. I said what it is, right? It's 180 minus 140 equals 40. So the exterior angle is 40 degrees, okay? Make sense? What's my name, Amadou? What's my name? Good. You say Juana, I have a question, okay. So the next part is central angles for regular polygons. A central angle definition is the angle that's formed at the center of the polygon by any two adjacent vertices. So You need to know the center of it and then just unite it with each of the vertices. So then you will get the central angle. And then we have another one over there, and then we have another one over there, another one over there, and another one over there. A total of, again, the number of sides a polygon will have. Now, let's start here and rotate back to where we started. That rotation around the center, the fixed point, is how many degrees? 360, right? So the sum of all central angles is 360 again. If I want to know the measure of one of them, what do I do? If you know all of them are 360, what do you have to do to get one of them? Divided by the number of sides or angles, right? And you're gonna get the one of them. So the measure of one central angle, 360 divided by n, the sum of all of them is 360. Again, n is the number of sides or angles in a polygon.
I have a question.
Go ahead.
I'm trying to find the most possible conflict of that.
Yeah,
What's the?
we can definitely get to that when we have a break, right? Because right now we are on 21, page 21.
I know,
Yeah, it's in your notes, a lesson one, right? So, example 5. Okay, do you have a question about this page, Sean? No? Okay. So determine the measure of a central angle of a decagon. So again, decagon, we need to know how many sides. Deca is 10. Okay. So the measure of a central angle, so just one of them. (360) divided by 10 is 36 degrees. Now here's sort of like a riddle kind of question, a little bit backwards. The measure of a central angle of a regular polygon is 45 degrees. How many sides does this polygon have? Sometimes the question is, what's the name of this polygon, right? Because it's the same thing. If you know the sides, you should know the name as well, right? So now we know the question is talking about a central angle, and we know the measure of that central angle, right? We are trying to find how many sides. So what we want is to unite these information in one formula that maybe I know. Is there a formula that unites central angle with number of sides and maybe something extra that I just need to know of these central angles? Pretty much, right? So the formula that unites them all is the formula we use for finding the measure of one single central angle, right? So one angle equals 360 divided by n, one central angle. So the central angle is, we already know what it is, it's given 45 degrees equals 360 divided by n. N equals what? Let's see. This is very similar to the backwards question with the income, right? And property taxes or home, help me out, housing costs, right? When you have housing costs at the top, income at the bottom, and then 0.32 over here, right? And sometimes the question was, what's the income? What did you do? You took the housing cost, and what did you do with the 0.32? Times it by 0.32 or divide by 0.32? Divide, right? So the same idea here. The long way to get there is, this is the proportion, so it's an equality of two fractions. You cross multiply them, so you get 45. I'm hearing something that's not class. Really? So loud? Oh, maybe they're showing something. Okay. Ooh, that's loud. Okay, so 45 times n equals 360, and then you have to isolate n, but it's connected with times 45, so you have to cancel multiplication. To cancel multiplication, you divide, right? So you always have to apply opposite operation to do cancellations, right? So divide by 45, divide by 45. So that's how you end up with division there. That's the math behind it, okay?
I was about to say, that's very complicated for the way that I did it.
Yeah, well, that's, sure,
I just like looked at the other question, and I kind of like just reverse engineered.
yeah, that's
that.
fine. Because your brains they already know math, all it is math, if the rules is pretty much taking what we already know and have is, putting it into different kind of formulas, right? But there's a lot of mathematicians out there that they argue is math already there and we're just discovering it, or we're inventing it, right? What is it? So it's what's 360 divided? Yeah, 8, I think. So yeah, 8 side. You can also times both sides by n, right? To cancel the fractions, right? You still gonna end up in the same situation, and then you divide by 45. Yeah, so if the question would have asked you what's the name of this shape, not how many sides, right? Right now we're done because we answered the question how many sides does the polygon have? It has 8 sides. We're done. We answered, right? But some question will ask you what's the name of it. So then you would have to say it's an octagon. So always be careful to answer to, well, yes, you can write it anyway, but make sure you circle the answer. Because if you circle octagon, you didn't answer the question. You're just putting a name, and then you're assuming, oh, this is what you're answering the question. You don't know what the question is asking you, right? Sorry? One more time? Yeah. Yeah, that's what it is. Yeah, it is. Yeah. I know, but what if I don't know Latin, right? Okay. So break time or you go to, yes, right, okay. So 8:09, 5 minutes, 10 minutes, how much do you want?
35 and a half.
That's too much. I don't have that much. I only have 5 or 10. 10, okay. 8:20. The properties of regular polygons. The first property, in a regular polygon, actually these two properties are exactly the same, but one is for an even number of sides and one is for an odd number of sides. If you do have a ruler or something that's a straight edge that helps you sketch something, it's going to help us with the diagram here. If you have a regular polygon that has an even number of sides, the diagonals that unite the opposite vertices, they intersect at the center of this polygon. And that center is actually the center of gravity. So imagine having this shape like as a disc in your hand. If you would put it on top of a, let's say, pencil, it would stay flat, right? Because the gravity is not going to pull it more on one side or another. That's called the center of gravity. So let's do a couple or even 3 diagonals. There's one. There's another one. And there's the center of the shape. And now for the polygons that have an odd number of sides, like if you want to get the center of gravity, you have to draw perpendicular bisectors from one, or perpendiculars. So if it's not a regular polygon, it's not going to be a bisector. Perpendiculars from the vertex to the opposite sides. Okay, because opposing to a vertex now, it's not gonna be another vertex like it was here, right? So here, so this vertex, there's gonna be another vertex opposing to it, right? So here, even if you would want to find the opposing one, it's not exactly in the middle, right? So for these ones, you have to draw perpendiculars. Here's another one. And you can use the corner of the ruler to draw it perpendicular. That's the best or easiest way. So where these perpendiculars meet, that's the center of gravity or the center of this shape. So you can find the center for this. So for example, even for that central angle, there's a central angle, there's central angles and so forth. As long as you have the center, then you can unite the center with each of the vertices and you can find those central angles. Okay, so now we can unite the first two properties with the property number 3, because once you have the center of a certain polygon, you can draw a circle either inside or outside of that shape with the same center. Okay, so I can draw a circle inside. We call the circle an inscribed circle. And notice how it touches the middle of each of the sides, right? When you draw it. And that's what happens with equal number of sides. I'm not gonna redo it here because it's the same shape. And you can also draw what we call a circumscribed circle, and now the circle will touch the vertices. And these two circles will have the same center. So each of these vertices now would be equally distant, right? Because our polygon is a regular polygon. It's the same thing for the polygon that has an odd number of sides. We can have an inscribed circle, so that means it's inside, okay? So inside, it will touch again the middle of each of the sides of the polygon. That's an inscribed circle. And then circumscribed would be touching the vertices. These points right there, they're equally distant on the circle. So each piece of the circumference of the circle is going to be the same size. So this arc is called a piece of circumference. This arc, that arc, that arc, that arc, that arc are all equal in distance. So imagine taking that circumference and divided by 5. Now, these two words, inscribed or circumscribed, all it does, it refers to inside or outside. But I can have an inscribed polygon inside a circle. That means the polygon is inside, okay? I can have a circumscribed polygon. That means the polygon is outside and the circle is inside. So depending with which word you're using it, it means one thing or another, okay? So careful with them. Now, these are the examples that you may see for these properties. Louis, this is example 8, actually, I messed up the numbering. So Louis wants to drill a hole in the center of these two patio tables for a large sun umbrella. Explain using geometry how Louise can find the exact center of each, right? So we're gonna explain using property 1 and property 2, depending on the number of sides. So the first patio table has how many sides? Let's see, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 sides, an even number. So we can find the center by drawing diagonals of opposite vertices. The center is at their intersection. Now choose a couple diagonals or 3, so 2 at least, right? And then 3 if you want extras. So Louise can find the center by drawing diagonals of opposite vertices. The center is going to be at their intersection. So opposite vertices, that's one diagonal. Another one, whichever you want, it doesn't really matter. They all meet in the same point, and that point is the middle, and that's where you drill the hole. Okay. The other one is, it's counted how many sides? 1, 2, 3, 4, 5, 6, 7 sides. So a heptagon, that's odd number. That means he can find the center by drawing perpendiculars from each vertex to the opposite side. So Louise can find the center by drawing diagonals, and here is by drawing perpendiculars from a couple of vertices to their opposing sides. The center is at their intersection. Perpendicular, perpendicular. Let's do one more. Another one, making sure, but the third one, you really make sure that they all cross, right, in the same spot. There's center. Sorry,
the circle on by way, but then you see
from a couple of vertices to their opposing sides. The center is at their intersection. I don't have. Okay, so the one, example 9, Theo works for a construction company. He needs to put 5 nails in a circular pattern so that they are spaced evenly. How can he use polygons to do this? Include a diagram with your explanation. Now, we're gonna use the third property here. We know that we can inscribe a polygon inside this circle, right? So, or even if you want, you put a polygon on the outside of the circle, whichever is easier for you. If you want 5 nails for this particular project, that means you should be putting inside the circle a pentagon, because the pentagon will touch with each of the vertex one part, like one point on the circle, right? Now, I need to make sure that I'm drawing it in such way that they're equally distant, right, to one another. And I would need probably some tools that measure angles, because without it, we won't be able to, right? So you would start with a fixed point, whatever you want, right, on your circular pattern. And then you know that from here, you would have to, like, imagine having a ruler. If you're a contractor, you probably have one of those rulers that are kind of like scissors, right? Like they just open and close, right? And then you would open your ruler to the angle that a pentagon will have, an interior angle of a pentagon. So now we're going to need to know what's the one interior angle of a pentagon. Even though I'm a contractor, I still need to know that, so I know what to measure, right? So what is one interior angle of a pentagon? One interior angle of a pentagon is 72. That's the central angle. So we will have to go to that, either the central angle or the exterior angle first, right? So we can do 360 degrees divided by 5, which we get 72. This is not yet the interior angle. This is the exterior or central. They're exactly the same measure. And what I want is to use down the 72 to find the interior angle, the one that forms right there at the vertex. So 180 minus 72 is 108. Yes, okay. So then you know the property of pentagons that helps us with this project is knowing the interior angle of a pentagon and knowing that pentagons will be inscribed in a circle, right? So we can also write that down. Pentagons can be inscribed in a circle. So let's imagine what 108 is. Approximately, you have your contractor, you use your rulers, and then you measure that angle, and then you draw 2 straight lines. So you say, okay, this is my 108-degree angle where my 2 lines cross the circle. That's gonna be where I'm gonna have the next nails. Right, and then you do the same thing. You already have one arm here. You're gonna draw another arm there, and you say, okay, that's 108. That's gonna be my next nail right there. Make sense? And it's gonna be, let's see, 1, 2, 3, 4. Now this is gonna be the fifth one. Approximately, that's pretty close, even without the protractor. Right? You did a pretty good job. But if you had the tools that have actual measurements, you will be able to measure the 108 with high accuracy. Now, is it the only way? Not the only way. You can do it other way as well, as long as you can inscribe that pentagon.
Base, you could, even more, as, almost, like,
Yeah.
whatever, like,
In real life, you would do that. The question said use polygons. So we had to use the
Yeah.
polygons for us for this
If
question.
it was like a circular case, then take a, long thing, then it can go around it, figure out exactly how much.
Definitely, yes, for sure, you can do that, for sure. It's actually pretty easy. I think if you would have those tools, that would be really good, easy and accurate. Sorry?
Why do they
No.
have DVDs?
Well, I don't know, maybe it has to be a certain pattern.
Companies don't make them space that.
No, right?
I just put it to you.
Okay.
Slam